So I will present you today through this webinar, as René said, three main workflows we use in doing our interpretations. They all go around the theme of pre-stack data, velocity handling, and the performing time depth conversions. First of all, I'll begin with presenting how we can display and use pre-stack attributes in OpendTect to do the interpretation. So after having looked at how we can display pre-stack data in the 3D scene, we'll look at how we can set up pre-stack attributes and create post-stack volumes from pre-stack data using the attribute engine. Secondly, we'll go in the second part on the velocity grading theme, where we'll see how to load stacking velocities and how to grid stacking velocities into volumes, or how to grid coarse volumes, coarse segue volumes into full resolution velocity volumes, and how to convert between RMS velocity types and interval velocity types back and forth. And the next theme in this webinar will be time depth conversion, where after looking at a tag we use in OpendTect to help us, we'll see the two main modes in performing time depth conversion. That is the on-the-fly time depth conversions of volume and horizons through a special OpendTect scene. And we'll go on with the batch conversion of volumes, the batch conversion of horizons. These two are separate, they use different facilities, and we will see how to set up a new survey to use the batch converted data in OpendTect into a new survey. But let me begin first with pre-stack attributes. I'll assume to start that pre-stack data has been loaded in OpendTect. And first of all, since the main OpendTect scene is a 3D scene based on inline and crossline positions, it's not yet possible to display pre-stack data. In order to display my pre-stack data, I first need to add an empty plane, an empty slice that is either an inline or a crossline. On that element, I can go in the interact mode, so showing the arrow here on the graphical toolbar, and I right-click somewhere on that plane in order to get that menu and look for the item called Display PS Gather, Display Pre-Stack Gather. This item will give me another menu showing the list of all the pre-stack data loaded in this OpendTect project. So I'll now select one with the mouse left-click, and that will display my pre-stack data for that position in the scene. Now if I go back to view mode, I can move around and look at my data. That's only one position, so if I look when moving the mouse over that plane on the position, I can get the inline and crossline value of that position. It is possible through this pop-up toolbar, pop-up window, to browse through the positions using the mouse wheel or the arrows over that window with a given user-defined step, 10, 20, and so on. These are the two ways to display your pre-stack data, either using this window that comes up when loading pre-stack data in a scene, that can be done in interact mode as well as in view mode, or I can go in view mode and drag and drop with the left mouse click this plane. If I go to another position, to another inline, it will take the plane with the pre-stack data attached to it. So both remain attached and both will be updated while moving the inline position or the crossline position, if that would be a crossline plane. Now this pre-stack data is not yet is yet as it is on disk and not really ready to be used in order to make any attribute. As we can see, we have quite some energy to mute in the first place, and we are losing quite a lot of amplitude with depth. So in order to alter this display, we need to look at the properties of this pre-stack display. The properties window is the following, consists of 4 tabs. The first one is holding the shape options. So it is mainly the width of this plane, the view side, left or right of the cross line. The appearance tab will concern mainly the color bar option. Scaling will be the amount of clipping we use, if we use clipping. But the most important method when it comes to displaying pre-stack data is located in the 4th tab. Here we have on the left a number of pre-processing methods, so attributes applied to the pre-stack data and that output pre-stack data that we can use for altering this display. What we can do, we can, for instance, input a mute, use a mute definition to remove the top part of this data set. So I'm going to the properties of the mute, and I've selected an already loaded mute definition. And by pressing apply, you can see how this mute definition has been applied on this position. What I can also do, I can add more than one step. I can add an AGC step, which will have the following properties, so window width and low energy mute. And where's my properties? Here. And I can apply it. So this will affect the, it will process an AGC on trace-by-trace basis on this pre-stack data. So the most handy tool to have here, once this flow of pre-processing methods has been set up, is the ability to save the setup, including the data locations and choice of parameters, into a pre-stack, what we call a pre-stack processor. I've reused an existing name for it, and that set of methods is now stored on disk. I could apply it to all viewers if, because it is of course possible to have several pre-stack displays at the same time. So I can apply this to all viewers. I can also save it as a default. Here we are. Now that is, now we are more or less done with the display of the pre-stack data. There's one more option that will be available in version 4.2 of OpendTect. On an empty plane like this, it is possible, when looking at the list of stored cubes, to display the pre-stack data. You'll see your pre-stack data marked with curly brackets. So without curly brackets, these are normal post-stack data volumes containing either seismic data or attributes or velocities. But we can also see the pre-stack data. If I click on the pre-stack data element, I'll get this additional window that doesn't appear for post-stack data. That is a selection of the offsets contained on the pre-stack data store. So I can select, like in any file browser, using Control and Shift click, several items, and when pressing OK, these items will be loaded individually as individual planes on that inline. If I increase a bit the tree size, we can see that the offset value is written here on this layer. And while being in view mode and having this item selected, if I move the mouse over it and press the keyboard arrows page up, page down, you can see how I can scroll through the different offset planes. So these are common offset volumes that we are looking at. If I would have loaded the data using angles, I could display common angle data in the same way, the very same way. So this is an additional way to display pre-stack data that you have available. Now for the creation of attributes, we'll have to go to the attribute set window, which is this icon in the main toolbar. And there is one attribute that is part of the basic attribute here at the sub-selection that is simply called pre-stack. That is the only attribute in OpendTect that can input, that can have pre-stack data as input and that will always output post-stack volumes. Well, it can do many things. First of all, it can rerun the processing setups we had applied previously. We had specified previously, so that is the mute and AGC, for instance. Not only it will apply these pre-processing methods, but it can also make a small an offset sub-selection, so between 400 meters and 2,000 meters. So these are values in the units of the trace coordinates. And as output, we have two main types. We have outputs of type statistics and outputs of type least square. The statistics, for instance, if I count all the values of my pre-stack data between these two offsets, I simply get the fault given my setting. If I average the collected value, I'll create a partial stack after the application of mute and AGC. And since there are many more statistics I could use, for instance, I could extract the standard deviation of the amplitudes, and that would be something like the stability of the stack, telling me how the amplitudes vary from offset to offset, once all values have been collected. The other large family is the least square calculation type, that will also extract the very same amplitude, but instead of outputting a statistical value, it will perform a least square regression between the amplitudes and the offset or the angular quantity. It is possible to apply transformation on the fly of either the amplitudes here or the x column, which is offset or angle. And the output will be our AVO attribute intercept in this case. I can also output the gradient AVO attribute. And I could, as a QC, output either the standard deviation of the intercept of the gradient or simply the correlation coefficient of the AVO least square fit. It is another kind of measurement, quality measurement as the stability of the stack. Now we have defined a number of attributes that we might save in an attribute set. Now I'll simply press OK to load these attribute definitions in memory. And now that they are loaded in memory, they are ready to be applied to any inline, crossline, or volume element in the tree. So for instance, on that inline, I'll apply my first attribute, that is the fault. So the fault is simply a count on the number of traces for which we have extracted data. And we can see that we have a quite constant fault. It's a syntactic data set. And we also see that because of the mute, we have a fault that is diminishing with the shallower depths. So the fault is really counting the data you have between your first offset and where the mute function is located. Now what we'll also do, we'll do a partial stack of this data. That was the second attribute I had applied. And that is that's giving us the stacked data. We can also check the stability of the stack. I said the standard deviation of the loaded amplitudes, of all amplitudes used to create this partial stack. And that gives me quite a different picture. That is for the statistics part, for the statistic calculation type of this pre-stack attribute. And I'll proceed to the computation of the AVO attribute intercept. That is not more than an extrapolation of the amplitudes to the zero offset domain. That is an attribute we can very quickly compare with the partial stack, so that is partial stack and the intercept, and that's quite the same. Also, the gradient attributes can be computed in the very same way. It is also, once again, a completely different quantity. And to end with these pre-stack attributes, I'll compute the correlation coefficients along that inline. We can see it varies between -1 and 1. That's an attribute that is a bit, once again, quite different from what I've called the stability of the stack. That would end the evaluation part of these attributes. Once the evaluation is finished, we are always free to proceed with the batch processing of these attributes. And in order to do this, we use the icon that is right next to the attribute set window, that is the one that creates seismic output in batch mode. So as quantity to output, I can choose any attribute in the list. There will be a default name provided, and then we can proceed with the batch processing of this data. That ends more or less the parts where I want to present what can be done with pre-stack attributes. So we have seen how to display pre-stack data in the 3D scene, how to set up pre-stack pre-processing methods, and how to create post-stack attributes from pre-stack data. Now in the second phase, we'll go more into the use of velocities into OpendTect. I'll use another survey for this purpose, F3 demo. And first of all, let me show you seismic data. So this is now a time survey that we are looking at from the Dutch North Sea. And I have stored stacking velocities on disk. The very first time we need to do is to import these velocity functions that are stored in a text file, in ASCII file. I'll go there and select Browse for my text file. It is this one, the following. And let's have a look at what it contains. The format must be the following. This input stacking velocity file must contain one position, so one x, y time value for each line. And then for each position, x, y time or depth, I need to have a velocity value attached. So if it is an RMS velocity, well, it is truly the RMS velocity at that position. If it is an interval velocity, it will assume that it is the interval velocity above this time or depth. So I have other data here. I could load the corresponding interval velocity, average velocity. I even have the depth. For now, we'll only load this part of the file into our function. So I have to specify that it is an RMS velocity that our input. When loading RMS velocities, I could load statics with it. So statics would have to be loaded using horizons loaded in OpendTect. This horizon contains two-way travel times for time surveys, and then the user would have to provide a replacement velocity in meters per second that corresponds to these statics. What a user can also provide is a velocity attribute grid in case the velocity varies with the position. In such a case, the horizon holding two-way travel times and the grid holding the velocities must be imported before we go to this import utility. But for this data set, there are no statics to apply, so let's go back to no. My dataset has a fixed header, one single line, and I need to specify the format definition. So X and Y positions are located in columns 1 and 2. I could use inlines and crossline instead. Z values are in column 3, they are milliseconds. Velocities are in column 4, and I don't have anisotropy values, even though they could be imported at the same time. And once I go out of this window, you can see that the format definition is now defined, and the only thing that remains to be done is to give a name to the output velocity function. So that is where I'll give simply this name. So this will be my imported VRMS functions. On pressing go, it will import this data in OpendTect. So import succeeded, that was the previous warning, and I can dismiss this window. Now I have dismissed this window, but so far there is not yet any data to visualize in OpendTect. The imported functions will not appear in the seismic manager because there are no volumes yet. So the first step to make right after the import of velocity function is, as I said, wrote in this PowerPoint, is to create the stacking velocities into a volume. So this is something that is a task assigned to the velocity, to the volume builder, which is also in the main toolbar, which has one specific step that is doing only gridding. So I'll use such a step, and we can see that it can perform either inverse distance weighting or triangulation gridding. If I need inverse distance, I need to specify a search radius, and if I want to use triangulation, there is here no parameter to specify. As a velocity source, I can input several types of velocities. Either I can use a volume which would not have values everywhere in the seismic survey, and that I want to grid, or it can be stored functions, which is what I've just imported, or velocity peaks, so residual move-outs. In my case now, I have stored functions, and I may select my previously imported stored functions, the VRMS functions. And the name of this step could be something like triangulation of VRMS functions. Okay, and this is one step of the entire volume builder creation. And I could add, after this triangulation step, any smoothing step, but that is not mandatory. So for now, I'll only create a new volume based entirely on the triangulation of these functions. So I'll now store this processing setup using a name like read velocity functions. And for now, I'll toggle off the option to process an OK. So I'll simply press OK now. That will put this definition in memory in such a way that I can apply it on any position of my survey. In order to have it applied on the fly, I use a special layer of these slices called Add Velocity Display. If I look at the right-click menu of a normal layer, it has many items so that enable me to display stored cubes or steering cubes, or to do other kind of settings. For this specific layer, I have far less options. The main option I have now is to select a processing setup for application on the fly on that inline. So that's what we can see here with colors. Let me change the color bar so that it is more easy to see. So this step has contains now the velocities as triangulated on the fly for that inline. and by default it has a non-zero transparency that I could alter. So I could back to a lower, to almost no transparency or very few transparency. So that is a way to QC the volume builder processing before computation on disk. Now that it has been QC'd, assuming that we want to go further and to batch process this setup, the best way to do it is to go back to the volume builder setup, to toggle on this option to process OK, and to press OK. That will bring us to another window, that is the batch processing window of volume builder setups. And the only last step or there's trivial step to do is that is to provide an output name for the volume to be created. But it is much more important to specify the volume subselection, because volume builder setups have a very specific, I would say, purpose, is they don't have yet geometries. In that respect, they can be applied everywhere, and before we process them into a volume, we need to specify the geometry, requested geometry of the output volume. By default, if we are going to use the output volume for time depth conversion, velocity picking, or this kind of workflows, we need to have data on every CDP location. So we'll need to use a step out, that is the step out of our preset data store, most often one or two. Concerning the vertical step out, this one can be more relaxed. We don't need to have to use the same sampling rate as of the seismic sampling rate. And that is quite important because it will control the amount of data that is stored on disk and in memory while working with the velocity volumes. So most often we'll go for a very low step out, lateral step out, and a larger vertical step out, like this. And now we can proceed, and that will launch the batch processing of this grading of velocity functions. Now I won't do this batch processing right now. I have done it already, and that will give me this RMS velocity volume. So this RMS velocity volume exists at every position of the survey because it was graded like this, and is ready to be used for either time depth conversions or velocity picking in OpendTect. Nevertheless, there are some applications that do not work with RMS velocities and that require to have interval velocities. If you really need interval velocities, we provide a utility to perform velocity conversions. So it is part of the processing menu here in Create Volume Output Velocity Conversions. We have the possibility here to take an RMS velocity volume and convert it into an interval velocity volume. There's one important step we need to make sure is that these volumes are properly tagged as containing RMS velocity values or as containing interval velocity values. This is because this batch processing utility will deduct the output type based on the input type. And the tag is something we'll see here in the edit field. So if I press edit, I'll see that, okay, this volume contains amplitudes that are VRMS values. Okay. If you remember, this tag is a tag I've set already here while importing the velocity functions. And when I've graded, when grading the RMS velocity functions into a new volume, the tag has already been set on the output volume. That is for the batch conversion of volumes. Now if I go back to the scene, once it has been batch processed, I can display the corresponding interval velocity volume. So this is the interval velocities that corresponds to these RMS velocities. Both were computed in the time domain and exist in the entire survey. Now that I have a velocity volume with values at every location in the survey, I can go further and perform time-lapse conversions in OpendTect. As I said before, there are two ways to do this. Either we'll use scenes to perform the time-lapse conversion on the fly, or we'll perform batch conversions. The on-the-fly time-lapse conversion are performed in separate scenes we can have here in this menu that are called simply depth scenes in this because this is a time survey. It will be called a time scene if we were in a depth survey. Now I need to specify my velocity model. I use now the interval velocity model with the same settings as before. There is a new option we have implemented in the incoming release of OpendTect 4.2 that provides a default depth range for the output depth scene. This depth range is computed by scanning through the amplitudes of the input model, of the input velocity model, where the software will compute minimum and maximum average velocities at the top of this volume and minimum and maximum average velocities at the base of this velocity model. And based on these four numbers that are the output of the scan option, we can provide to the user default values for the output depth domain. And these numbers are only suggestions. I'll always be free to choose either one of these numbers myself or to use any other value. Okay. In 4.0, the computation is a bit less accurate, but still we have implemented some intelligence to get the Z range. Now in this new scene that is still empty now, I can add my default data. That will be my time seismic data set, this time now converted on the fly into the depth domain. So the values I see in the status bar here are now depth values, so X, Y, and depth value. Okay. I can also display my interval velocity model. That is stored on disk in the time domain and that is converted to depth on the fly. And I could also load most of the 3 items you see here. So I could load cross lines, time slices, or horizons, but no wells. So this is mainly a tool done to very quickly check if the time depth conversion gives something reasonable. And once we are okay with the on-the-fly conversion of the velocities, most often we'll want to batch process our time volumes into the depth domain. For the batch processing of volumes, we'll go into the processing menu, create a volume output, and perform the time-lapse conversion here. So the directions are either ways, time to depth or depth to time. We'll provide once again the same velocity model. We'll select a seismic, any volume loaded in the project in the time domain, and provide a name for the output depth data. Like I said before, in version 4.0, you need to specify a depth range whereas in the incoming version 4.2, the depth range will be provided from the scan output of the velocity model. And once again, I'm free to round off these numbers to any value. And then I can press proceed and do this depth conversion on the fly. The depth volume will be stored within the same survey in the time domain. So if I look after it, it looks like this. So I can see very easily it is tagged here as being a depth volume. Most other volumes do not have this tag, which means that they are in the depth domain. Once again, the presentation changes a bit in the 4.2 release, where we simply write out time range for time volumes and depth range for depth volumes. That is for the batch conversion of a volume. Once the volume has been converted into batch, it can be displayed in the depth scene. So I'm back now to the depth converted scene using this option here, which is depth data. So the stored cubes here are in the domain, the default domain of the survey. These volumes are all in the time domain. And the depth volumes in this time survey will be listed will be specifically listed in this item here. And the main difference between these two is that one is computed on the fly, whereas the other one is really the data stored on disk that we are looking at. And the opposite is not true. It is not possible to display in the normal scene, so in the time domain, the depth processed data. In order to and before I'll show you how to display the depth data in a normal scene. I'll first show you how to batch convert the horizons. So I'll go to Survey, Export Horizons ASCII. And I've selected, there's a default horizon selected here. I'll put XY locations as usual. And most often when outputting an horizon, if I say, if I use the option yes for output Z, the output Z values will be seconds or milliseconds in the time domain, as it is on disk. What I can also do, I can perform a transformation of the Z values while exporting this data and perform my transformation to time to depth conversion using a velocity model. The output in this case is either in meters or in feet. And the output will be an ASCII file we can load in a new depth survey. Once again, before we go to the depth survey, I'll show you one more new option in 4.2 concerning this export of horizons, is that you can do the conversion using not only velocity models, but also using either a linear trend, so V0K, or using the depth time model of a loaded well, like F3 on this data set. So now we are more or less done with the batch conversions. So we have, let's say we have batch converted our volumes, we have batch converted the horizons we want to have in the new depth domain. Now the best way to use the batch converted data is to set up a new survey in the corresponding scene. This can be done by going to Survey Select Setup, so it is the very first icon here, and we'll create a new survey based on the input time survey that I'll call F3 demo, let's say depth, and I'll copy all the geometrical settings from the previous time survey, which is listed here, which is this one. And the only thing I need to change is the Z range. Most important to change is the domain from milliseconds to meters, and I may want to affect the range as well as the sampling rate. Now I can press OK. I can see that the output, the new survey has been created, but so far it's an empty survey, so there are no loaded volumes, no loaded horizons. That remains to be done. I'll increase a bit the Z range to see the data a bit better. And now the first thing to do is to import the seismic data. This will be done by importing the CBVS volume that has been done while batch converting the volume from time to depth. So I'll browse back to the time survey and select my depth data, which is here. I have to remember its name. And I'll use most often the option to use the data in place, which means that this file will remain on disk in the time scene and will be referenced in this new survey. So I could, the reference name is the following, and that is something I can change, I can alter while loading this data. And I press go. And right after we have done this, we can open the Seismics Manager and see once again, so that is my data. So it is physically in the time survey, it is still the same file on disk, but I can go here on a normal inline and display the data. Another thing we can do, we can also try to access. Well, let me first also. I'm afraid. Yeah. We can also import the horizons. I won't do this now because I didn't do the batch processing yet. But we could import the horizons in the very same way using the import of ASCII horizons. What is more interesting to do is to reload the velocity volume we had in the time domain. So I'm now in the depths scene. I'm trying to import a time volume in the depth survey. Once again, I'll browse back to the time survey, and I'll look for my velocity model, which is this one. One option that is not in 4.0 but that you will see in version 4.1 and later of OpendTect is that I now have the possibility to tag this imported volume as being a volume that is in the time domain. So I'll press go, and now that this has been done, so I can display. I won't see my velocity model here in the normal scene because this is a depth survey. So I cannot see my time data in the depth domain. What I need to do, I need to create a new time scene in the depth survey. But in order to have a time scene in depth survey, I need to specify a velocity model. And if I press on select, there is no velocity model yet set up. That is what you'll see for each new survey. You'll see that the new the loaded volumes are not tagged as being velocity models. In order to tag loaded volumes as velocity models, we need to press the option Create, browse through all the stored volumes in this depth survey, select the volume, tag it, and only then we'll have a velocity model. Now I can go back into edit and perform the scan I mentioned. So even for this file is 1 GB large, the scanning is most often rather quick process, and that will give me more accurate time ranges for the conversion back to the time domain. It is very important to keep these steps in mind. First of all, while importing data, we have to specify if it is a data in the time or in the depth domain. The default will be the default domain of the survey. And if the data is a velocity model, it needs to be tagged at all locations where velocity models are requested. So that is when grading velocities in the volume builder, that is when creating time depth scenes on the fly, or while performing time depth conversions. Eventually also picking velocities. The scan is almost finished, and we'll see the updated values right after the end of this scan. Okay, so the values have been updated considerably. And now if I press OK, we can see that the time range is updated. So I'll use the input time range we had before, and that will give me this time in the depth scene a time survey. The main point I would like to stress here is that even regardless of the survey being in the time or in the depth domain, velocity models can be of either time or depth domain, and they can be always used regardless of their domain for performing time depth conversions, velocity conversions, and all the steps related to these interpretations. Now in this time scene, I can display either my stored data, my stored seismic depth volume, that is this one, or I can also show my velocity model in the time domain, which is this one. And now we are back to our feed, if I should say. We have seen how we can go from time data stored on disk, create scenes to see on the fly data either in the time or in the depth domain, how to set up a survey that is natively in depth, and how to display the time data back in this depth scene. And this concludes this webinar on pre-stack attributes, velocity conversion, and velocity grading and time depth conversions. If you have questions, we'll be free to answer them.
Well, thank you, Arnaud. Actually, we've had quite a few questions. This has been a very busy panelist time this time. We have a few questions that we would like to go ahead and have you answer. So I'm going to find them real quick, and I will forward it to you so that you can read, but I'll also try to read aloud if you would like that. So the first question, here you go. It says, regarding the pre-stack AVO attribute calculations, for AVO, don't we assume that the amplitude is linear with the sin squared angle? And, or do you see it now? Excuse me, sign.
Yes, I see it now.
Yeah.
Yes, that is something we have to assume in order to fulfill this equation. And well, it all depends on how the data has been loaded. In order to have the data extraction done in the same way as this equation, we have to have the offset values converted, and it means that you have to have as well offset parameter your angle and not offset, or the sine square of the angle in the trace headers used when loading the seismic data, the pre-sec data. So in order to be really in line with this assumption, because we do not provide yet the tools to do an x-axis transformation that is the sine square of the angle, but we have the quadratic or the square root of it. But the quantity below the square root must be converted in a different way. That is something we have in mind, and that we may want to implement further, but it has not been done yet. I guess
Okay.
it answers the question.
Okay, I will wait to see if anything
Yes.
pops up about that. But I do have, I forwarded actually a series of questions to you from the same asker. So you may want to
yes.
Yeah, you may
for converting time to depth, is it necessary to use the velocity model? For most items I've shown, it is necessary to have a velocity model. So stored volume, a volume stored on disk with positions on every CDP. But as you can see in version 4.2, we are trying to broaden the perspective and the field of application by enabling the time depth conversion using either V0K trends or TD models from wells. So the first implementation contains only the possibility to use velocity models stored on disk, but it will become broader already with version 4.2 of OpendTect. And
Yes. See, do we have any people who would like to ask questions verbally? Please raise your hand. See, I will be watching. If you would also like to type in your question and have it read aloud, we can do that. Otherwise,
one thing I may want to mention is that the volume builder is the one tool we use to create velocity models. And in version 4.2 of OpendTect, there will be a new grading step available, which I'm showing now, right now. That will be an horizon cube well interpolator. So this grading step will take well logs and will grade well log amplitudes in order to create a new 3D volume. And these well log amplitudes could be DT models loaded as logs in the OpendTect wells. And they will be interpolated between the wells by using an inverse distance or triangulation algorithms. For wells, most often inverse distance will be the one solution to use. And the horizon cube is an OpendTect object. It's a new plugin we are going to release with version 4.2 of OpendTect. That is a set of coarse or densely tracked horizons. So this will be a quite new grading, quite important grading step that allow the creation of depth time models from well data grading between horizons. And that will certainly be a method more robust than to use the DT model of a single well.
Okay, and we've had another question come in. I forwarded it to you as well, but I'll go ahead and read it aloud. It says, when gridding the velocity function, what is the difference in VMB results when using either inverse distance or triangulation algorithms?
Well, first of all, we'll expect most often medium to large differences between the two. These methods are rather different, and I would say that triangulation is the one method to prefer if the input data is at least laterally regularly picked. So if I have a volume that has a coarse volume with data on every fourth or eighth inline crossline, the method of choice for its grading is triangulation. On the contrary, if I have a very coarse set of input velocities, so that is most often the case with well data, where we have very sparse selection of wells that are really not regularly spaced geometrically, then inverse distance spacing is the method of choice. But both both most often need to be compared before we select the best.
All right, well, thank you. And the asker of the question replied, thanks, with a couple of exclamation points. Let's see, we have another question that came in asking about, can you please explain a little about building AVO and AVA attributes?
Yes, the main parameters are in fact when loading the SegWi data. A pre-seg SegWi data has a rather specific setting. I need to get some seismic data to go to the next step. In the SegWi import wizard, there are positions stored in the trace headers. I define the position of the points on this. So inlines and crosslines are x and y coordinates, and offsets and azimuths. The offset byte here is the one where we need to have the amplitude defined. And this amplitude can be either the offset value in meters or feet, it can be the angle value in degrees, or it can even be the sinus square of the angle. And in order to have the pre-seg attribute do a regression in the same sense as the Shui equation, the amplitude found at these byte locations should be the sinus square of angles. And therefore, this is something that that is either present in the SegWi file or that has to be done beforehand. But even though we have plans to enable the interpolation of a pre-seg data store to that domain, it is not something we have yet.
Okay. Well, thank you for answering that. And we now have another question. Can you generate a time slice from the pre-stack data, either from a line gather or a constant offset?
Yes. Yes, definitely. These options, I need to go back to the other survey. but here you can see that these volumes remain available for these elements. Apparently not in 4.0 it is not yet possible, but in 4.2 it is. And not only is it available for displaying purposes, but they are also available for computation purposes in the attribute engine. So for instance, if you would define an attribute of type energy, oh, sorry, I thought that was possible, but it's not possible anymore. No, sorry. Apparently, it's only available for displaying purposes. But you could have it on a time slice. Not in this survey, where I don't have preset data. Here, so the same offset subselection. Well, the data set has only 3 inlines. That's why the display will not be very nice. But yes, it is enabled for time slices as well.
All right, wonderful. Well, I'll wait just a moment longer to see if we have any more questions come through the questions pane, or if anybody raises their hand. But as we're waiting for that, I'd like to go ahead and thank our panelists who have done a great job of answering the questions during this very active webinar. And we do have another question coming in. It says, is the SEG SALT model one that you have at your download site?
No, it is not available on our download site. But yeah, on some occasions we might make it available. If request, it is something you could send. You could send it to me by email. I have a very small part of the entire data set available, but it's enough for working with it. We have, by the way, another preset data store that will be on the OpendTect seismic repository that would be more handy for use because it is real data. It is not synthetic data. I don't know if that is what people are looking for, but on the OSR, it is the survey called Penobscot 3D. This one contains 3D seismic data, migrated pre-stack 3D data, and also 2D pre- and post-stack data. So it is really the data of choice for performing these workflows. There is also a set of velocity functions that can be graded by the user after the download of this Penobscot survey. So I would really recommend to go for this survey instead of SEG SALT.
All right, well, great. Well, I'd like to go ahead and as I said before, thank our panelists and, of course, thank our presenter. And we're having lots of things coming through right now saying thank you, thanks, excellent presentation. So I think everybody was quite pleased today. And as I said before, the next webinar will be in February, where Farouk will be presenting crossplots. So if you try to log on in January, you won't get one. But in February, please join us again, and we'll send out links and invitations to that. And if you have any suggestions for future webinars, then please feel free to email anybody at DGB, and we will try to arrange what everybody wants. So thank you for joining us, and see you next year.